Hello, everyone. I assume you all had a very nice weekend. So from this week, I will deliver the online lecture from the lecture 6 to lecture 10. So today I'm going to talk about isotropic flownets and anisotropic flownets and how they can be useful for geotechnical engineers. In particular, we are going to learn a few tricks about how to draw them and some pretty cool calculations that we can do with them. So some good references are the lecture notes and also the classical soil mechanics textbook. So previously, we could use the Darcy's law to compute the seepage of water from the soil. So it's applicable for problems with simple geometry and boundary conditions. But in the real world, the problems are not simple. So rarely do we know the distribution of the height through a soil mass. So here in the top, that's the soil dam. And obviously the water was retained in the left-hand side of the dam. So due to the height difference, there's a tendency that the water flows from the high water height to the low water height through the dam and the ground. So in lecture 3, you have learned the Laplace equation for isotropic material. So if we know the boundary conditions of this case, for example, if we know the water level upstream, and also the water level downstream, then we can use the law of conservation of mass. Another way to think of this is what goes in must comes out. So we can use that law with a differential equation to find the height distribution through the soil. The Laplace equation could be pretty useful because we can solve for different pieces of total height at any x and z coordinate combination on cross section of a soil profile. So by solving this equation, we could get the distribution of the water height, the flow length, and pore water pressure, and even the total seepage. So this is a very useful equation, and which I will show you in more details in the coming few slides. So the Laplace equation could be solved for a known, or constant height, and then if we were to contour these different points of equivalent height, we could call that contour line an equipotential line. So any point on this equipotential line, the water height will be the same. It's remained constant. So by definition, on an equipotential line, the water height h is a constant. So for any point on the equipotential lines, since the water height h is constant, so any increment in h, and this obviously that's 0. So the slope, and this formula is valid. So this formula is valid. So through the mathematical transformation, the slope of the equipotential line is given by dz over dx. So that will be equal to negative partial h over partial x divided by partial h over partial z. So we have this expression. And another equation could be solved and similar to the Laplace equation, but perpendicular in essence to the equipotential lines. So we call these the flow lines. So those are the flow lines, because they represent the path that a drop of water would take to travel through the soil. So at any point on the flow line, we have this relationship. So also from Darcy's law, we know Vx equals to Ki. Vx equal to Ki. And also for which the I is the ratio of the change in height over the changing in length, or the partial h over partial x. We have the negative sign here because we need to capture the fact that we are losing the height and the water flows through the soil. So it's not gaining. So that's why we need to put a negative sign here. Similarly, Vz is also equals to negative k times partial h over the partial z. So the slope of the flow line is given by partial h over partial z divided by partial h over the partial x. So by now, we have two expressions. So this expression, one expression for the slope of equipotential line, and then one for the slope of flow line. So if we multiply those two expressions, then we get a value of -1. So obviously, this one multiply this one, we get value. So what does it mean? So it indicates for isotropic material, the equipotential lines and flow lines are orthogonal. So which means they formed a right angle at any intersection point. So obviously, this is a flow line, this is equipotential line. So they form a right angle, anywhere, right angle. Can you just mute yourself? So otherwise, I have to force to mute.
Oh, sorry.
Have you mute yourself? This run. Okay. So everyone in the class, just try to mute yourself. Later on, we'll allow you sufficient time to answer any questions. Go to page 8. So to have floating. So and then the flow lines and equipotential lines together, they form the flow lines. So we call the combination of the flow lines and equipotential lines, that's flow line. So let's have a look at geometric properties of the flow lines. So consider a pair of flow lines. So that's FL. So that stands for flow lines. So that's one flow line. That's another flow line. So they intersect with the equipotential lines. So that's one equipotential line. That's another equipotential line. So clearly, the flow through this flow tube must be constant. So as the tube narrows, so from the right-hand side to the left-hand side, the tube will gradually narrows, and the velocity must increase. So only in that way, we remain the constant of the flow. So for the small element, SYZT, so only this one, SYZT in the left figure. So suppose that flow per unit width. So by saying per unit width, I mean is the unit width in the direction perpendicular to the screen. So if you know what I mean. So if so assume, so actually this is just like a cross-section view. So normally, so here there's a unit width, normally maybe 1 meter. So you have, assume you have 1 meter perpendicular to the screen and into the screen. So that's so-called unit width. So suppose that the flow per unit width is 30 cube. So the velocity in the tube is given by v equal to 30 cube over absolute yx. Because you have the q equal to va, and a that's a is equivalent to yx absolute value yx times 1, because unit width, because you consider this cross section and yx. So that's the cross sectional area. So that's a. So that's why v equal to 30 cube divided by absolute yx. And also from Darcy's law, we know v equal to ki, and I also equal to 30 cube, 30 h divided by 30 l. And in this case, the 30 l is zt. So that's 30 l zt. So that's the length along the head drop. So by transformation, by combined with those two formulas, we got this relationship. So delta Q over K times delta H equals to absolute Yx over absolute Zt. So we have this expression is valid for the small tube. And then similarly, when we consider the large element, capital X, Y, Zt, this one. So the velocity in the tube is again, velocity in the tube is given by V equals to delta Q over absolute capital Yx. And also from Darcy's law, V equals to delta H divided by absolute Zt. So this is quite similar to the small element, but it's also valid for the large element. So according to the previous two expressions, we can derive, we can get the same similar formula, delta Q divided by K delta H equals to absolute capital Yx divided by absolute capital Zt. So now when we list, so now we already get the expression for the small element, and also a large element. So these are some typical elements within a flow net. So if we list both expressions together, so this one for the small element, that's for the large element. So because the left hand side, the term are the same. So we have this relationship. So we can find absolute Yx over absolute Zt equals to absolute capital Yx over absolute capital Zt. So therefore, we have the conclusion that each of the elemental rectangles are bounded given by the flow lines and equipotential lines, and they have the same length to breadth ratio. So all these derivations help us to draw the to find some common characteristics of the flow nets and help us to draw the flow nets accordingly. So next, we consider a pair of equipotential lines cut by the flow tube. So now originally that's the two flow lines, but now there's two equipotential lines, and they intersect with the flow lines. So that's the flow line, and that's the flow direction. So obviously this is the higher water height, that's the lower water height. So there's a tendency for water to flow through the tube in this direction. So if it's assumed that each tube is of unit width, so the same as before, so it's in the direction perpendicular to the screen, then for the small element ABCD, so that's the ABCD, that's the small element. So for this one, we have this relationship, V equal to delta Q divided by absolute CD. So this one. And also from Darcy's law again, so V equal to K times delta H divided by delta L. And this time delta L equals to absolute AB. So we have this relationship. And then next, we're able to get this relationship based on the above two formulas. So delta Q over K delta H equals to absolute CD over absolute AB. So similarly, when we consider the large element, capital capital ABCD, capital ABCD, the velocity in the tube is given by V equals to delta Q over absolute CD. And from Darcy's law, we have this relationship. So again, by the transformation, we get delta Q over K delta H equals to absolute CD over absolute AB. So similar as the previous case. So when we put those two formulas, so one for the small element and one for the large element together, we have this relationship as well. So hence, a pair of flow tubes carrying equal flows will intersect a given pair of equipotential lines in elemental rectangles, which have the same length to breadth ratio. So all these conclusions help us to draw the flow nets. So in drawing the flow nets by hand, it's usually draw them so that each flow tubes carries the same flow. So the head drop between the adjacent equipotentials is equal. So in these cases, all elemental rectangles will be similar. It's usually most convenient to draw the net so that the rectangles are square. So normally we can't make it exactly square, but we try to make roughly like a square shape. So each rectangle, we try to make a square shape. So, and also, so it's possible to draw an inscribed circle because it's square. So obviously we can just accommodate a circle, and it's just a tangent with the 4 edges of the square shape. So that's the rule we have to follow when we draw the flow nets. So in most problems, we know the head difference between the inlet and outlet. So delta H equals to capital delta H divided by the number of equipotential drops. So normally for the problem, normally the water head upstream is already given. So for, let's say, for this example, the water head in the upstream, so it's this level here, that's 18 meters. For the most problems, it's already given, so that's 80 meters, because we know how the depth of the water retained by the dam, and we also normally know the water level downstream, because the water was retained, so normally the downstream water height is normally 0. So then we know the head difference, that will be per H equal to 18 minus 0, so that's 80 meters. So we know the head difference. And so the delta H means the head drop for on each equipotential lines, then we are able to get the value. So for this case, the flow net has been provided in the chart. So obviously those are the flow lines. So each flow line, that's the flow line, and that's the equipotential line. So we count the equipotential line for the head drop. So that's we count from here. So that's the original water head. So that's 1 head drop. So that's 2 head drop, and that's 3, 4, 5, and that's 6 head drop. So in total, that's there are 6 head drop. So each head drop, it will be their H will be 18 divided by 6. So each head drop will be 3 meters. 3 meters. So that's why the first water head, obviously that's 18 meters. And the second equipotential line, the water head will be 18 minus 3. So that's 15 meters. So we follow the same way. We are able to label all the water head value for each equipotential line. So, and also for this question, the permeability that's given, K equal to 10 to the power of -6 meters per second, and the width of the dam, that's 25 meters. So if the datum for the calculation of the head is taken to be the base of the dam, so normally the datum is taken as here. So that's the datum. No, it's here. Actually, for this case, it's here. It's datum. But actually, if you take the datum here and take the datum here, it will be the difference, because the head difference will be the same. So if you take the datum here, then the downstream water head is 0. If you take the datum here, then the water head is just only the distance from here to here, and upstream the water head will be from here to here. So if this part will be cancelled out, so your head difference will be the same. So no matter where you take the datum, but normally we take the downstream level as the datum. So here you need to be aware of that. So the flow net, since the flow net has been drawn, so the elemental rectangles are approximately square. So roughly each rectangle roughly square. So that's the so we have to meet the requirement or conclusion.
I can't hear you.
Can any other student hear me?
Mute.
Tiny user.
Yeah, we can.
Can you hear me?
Yep.
Oh, I can hear you.
Okay, that's good.
Tasu, how do you find NF? The number of flow tubes.
Sorry, maybe just let me continue, and then maybe you keep a note of your questions, and then we can go back and address all together. Yeah.
No worries.
So we just work more efficiently. Okay. So inspection of this figure shows that there are 6 equipotential jobs. So we already count that.
Can anyone hear the teacher? Guys?
Yes.
Yes. Can you
Yeah,
just,
I can hear him.
Yeah. Can you just try to mute yourself?
Okay, thank you.
Yeah. So there are 6 equipotential jobs, and so the head job between each pair of equipotentials are dirt hedge. So that's 3 meters, and then the NF that stands for the number of flow tubes. So that answers your question. So NF that's the number of flow tubes.
But like so
Yeah.
how do we find
So,
NF?
Yeah, so NF we count this way. So we just count. So once you draw the flownet, you just normally count from the any part in the left hand side. So if you count from this action, this area, so 1, 2, 3, 4, 5. So
okay.
the flow tubes will be 5. Or if you take this one, 1, 2, 3, 4, 5. So
yeah, no matter what, it'll be the same number.
Yeah.
Okay.
Yeah, NF stands for the number of flow tubes, and it's 5. So, and ND, that's the number of head jobs. So it's 6 in this figure. So this one, that's a really important formula for this lecture. So we have to remember this one and also be clear about the physical meaning of each parameter within this formula. So K, that's the permeability of the soil, and NF, that's the number of flow tubes, and ND, that's the number of head jobs, and dirt edge, that's the head difference between the upstream soil and downstream soil.
Excuse me, sir.
Yeah.
Sorry, but can you explain a little bit about the delta H a little bit? Like, I get it why we have that delta H is 18 minus 0 is 18, but
yeah.
But why do we divide for 6?
So if you don't know this H, then you don't know the value on each equipotential line.
Oh,
so you, yeah.
So that means we're gonna count from, for example, like 3, 6, 9, 12, 15. So
yeah.
we know that each of them is separately 3 meters. So
which means firstly you have to draw the flow nets, right? And then you need to use the flow net to do the calculation. That's for either for the seepage or for the pore water pressure. So if, let's say, if you for pore water pressure calculation at any point, then you need to know the water head at this equipotential line. So if you don't know the dirt edge, you don't know what's the value of water head for this line. So you have to do the calculation and then calculate the corresponding value for the equipotential line.
all right, I think I get it.
Yeah.
Thank you.
Yeah. Actually, yeah, this one, maybe this is the continue of the last one, the last problem, last question. So for this case, the dirt H, capital H, obviously that's 18 meter. Permeability, K, that's given. So if we put the magnitude of each value to this equation, then we could get the value of dirt Q and also the value of Q. So because this is unit width, so that's the Q. This is only the seepage for the unit width. By saying unit width, I mean the length perpendicular to the screen. So that's only for 1 meter dam. So but we are required to do the calculation for 25 meter dams. So in total, that's 25 meter. So in total, for your Q calculation, so you have to multiply 25, and that's the final value we need to get. So that's the unit is cubic meter per second. So who make the drawing here? The 6. The 6, that's the number of head drops. So we already count that from the previous slide.
So the value of 6 comes from the vertical line?
No, that's from the number of head drops. I think I have a, I wonder it's gone somewhere. Here, you see, the ND, that's the number of head drops, and NF, that's the number of flow tubes. So number of flow tubes, 1, 2, 3, 4, 5. And number of head drops from the upstream to the downstream. So from here to here, that's 1 head drop. And from here to here, that's 2 head drops. And 3, 4, 5, 6. So that's how we get the number of 5 and 6. Is that clear?
Yeah, thank you, sir.
Yeah.
Sir?
Yeah.
What is the difference between Q and delta Q?
This one?
Yeah. So what's Q and delta Q?
No, this is Q only. So this third Q is only the C page only visit for one small tube.
Okay.
And this Q, you see, that's because we have NF tubes. So each the tube, the flow will be the same. So we times 5 because NF that's 5.
Okay. Yeah. The very end with 2 times by the width of the dam.
Yeah.
Of Q. Yeah.
Yeah.
Okay.
Yeah. Yeah.
Yep.
Let me see whether I can just use my eraser. No, it doesn't work from my side. Oh yeah, thank you. I don't know who will just label that. So the above is the calculation of the C page, calculation of flow. So the previous case, the Q, that's the C page calculation for the Q. So for the majority of assessments, you will be required to calculate the Q. So this Q, you have to use this formula. So this is a really important formula. So in the later part, we have the question to help you to digest further. And another important part is to calculate the pore water pressure, U. So pore water pressure, U. So the pore pressure at any point can be calculated using the steady state flow equation that we have learned in the lecture 3. So after you you plot the flow nets, you can calculate the pore water pressure at any point within the dam. So let's say for this question, we are required to calculate the pore water pressure at this point P. So I label here point P. So this P is vertically 5 meters below the dirt, because originally we know the dirt is here. So that's 5 meters below the dirt. So in lecture 3, we have learned the total height that's equals to the sum of the pressure height and elevation height. So that's really important, another very important formula we have to fully understand. So this is total water height, and that's also equivalent to any value on the equipotential lines. And this is the pressure height, and this is the J is the elevation height. J is elevation height. So the elevation height is only has the correlation with the delta 0. So it's the vertical distance with the 0 precision. So obviously this point B, that's 5 meters below the delta. So the J will be negative 5 meters. And the water height, because this P that falls on this equipotential line, so we know the total height that will be 15 meters. So H is 15 meters, J is negative 5 meters. So if we iterate both values into this formula, this gamma W, that's a constant, that's 9.81 kilonewton per cubic meter. So we're able to calculate the pore water pressure. That's 196.2 kPa. So that's a really important formula. Once you get the flow nets, you are able to calculate the pore water pressure at any point within the dam. So now let's have a look at the common boundary conditions. So for the interface, so that's the so-called interface. So for the interface, between the water, so that's the water retained in a reservoir or dam, and the soil, since the total height at the indicated surface position is calculated as H equal to UW divided by gamma W, same as the previous formula. And by definition, for water pressure definition, we know U equal to gamma W H. And this H also equals to, so let's say for this point, at this point, the pore water pressure, the total height, this total height formula is valid. And at this point, the pore water pressure, we just calculate as gamma W times H. And this H, that will be from the water surface to this position. So that's H minus J. So if we iterate this UW to this formula here, then eventually we get this relationship. The small h equals to capital H. So that's the water height, which means if we translate that, the water height at the interface between the water and the soil, that's a constant. So it's all equals to the H, capital H value. So the water height and any position between the water and soil, that's the same value.
So
yeah.
So what's capital H?
The capital H, you see, that's the height. That's the height between the datum to the water surface, capital H.
Okay, thank you.
Yeah. So the upstream face of the dam shown in the previous figure is an example of this situation. So the water height at the interface, that's a constant, right? That's the water, that's H. You see here, that's the water and that's the soil. So that's the interface between the water and soil. So any point on this interface, that's constant. So that's H, capital H, that's 18 meters. So that's why the H, that's 18 meters along the upstream datum. And along the downstream line, that will be the same. So another special case is the boundary between the permeable and impermeable material. So this is a permeable soil. An impermeable material, normally it has either is maybe rock, ROCK, either is rock or just a clay. Because clay, the coefficient of permeability is very small. So normally we can take that as impermeable material. For sand, is normally permeable material or permeable soil. So for impermeable material, that's a clay and rock. So for the interface between the permeable soil and impermeable material, so that's the interface. So obviously the velocity normal to the boundary. So that's the interface or boundary. So the velocity normal to the boundary, that will be 0. So because otherwise there will be water flowing into or out of the impermeable material. That doesn't make sense. So the Vn or the velocity normal to the interface will be 0. So there's only the velocity along the boundary. So only along the boundary. So which means the boundary between the impermeable layer and permeable soil, that's a flow line. So that's a flow line. So maybe why do we have? So assume, you see, let's say for this dam, so the below the dam, assume that's the clay. So that's the clay. So that's the soil. That's the, let's say it's a sandy soil. Then this line, that will be a flow line because the water can only flow along this line. It can't be perpendicular to this line because it's an impermeable layer underneath. So that's the interface between the permeable and impermeable layer. The boundary will be a flow line. So that's two important conclusion we can refer to when we draw the Flownets. And then the next one that will be And next one, sometimes a proportion of the saturated soil. So this is for the earth stem, EARTH, earth stem. But normally this is there are only few earth stems in the field. Normally, just you see people, the engineers, they construct for the big dam. They all use the concrete dam, so they don't have such issue. But for some earth dams, they have some special issues. So we are going to talk about. So for the earth dam, sometimes a proportion of the set. Can you just try to mute yourself? Let me see. Mute all. Okay. So for the earth dam, sometimes a portion of the saturated soil is in touch with air. So the pore pressure of the water just beneath the surface, beneath this one, that atmospheric. So the phreatic surface shown in the figure, this one is called phreatic surface. So it's a flow line, and it's example of this such situation. And now, since we have this formula, the total height formula, so the delta H, the any increment in delta H, so delta H equals to delta UW divided by gamma W plus delta Z. So this formula is also valid. So because at the phreatic surface, the pore water pressure that will be zero. That's the water. That's the upper level of the water. So pore water pressure, that's the zero. So delta H will be zero. Sorry. So delta H, because the pore water pressure is zero. So here, this term, that will be zero. So eventually, we get delta H equals to delta Z. So this means the vertical drop between equal potential lines. So that's the equal potential line. The vertical drop between equal potential lines are equal for the phreatic surface condition. So this is one conclusion. Another conclusion we need to learn as well. So the phreatic surface, as indicated previously, that's a flow line. So it's also a boundary between the saturated soil. So let's say if this is a phreatic flow line, that's the saturated soil. That's the unsaturated soil. So saturated soil means the void is all occupied by the water, and unsaturated soil means between the soil particles, partially there are some water and partially there are some air. So that's unsaturated soil. Casagrande and Cozzani suggested one method or approximate method for to draw the phreatic surface of a dam with the toe drains. So they propose a method to draw the phreatic surface of the earth dam. But firstly, we need to find the upstream toe here. So that's the because water was retained in the left-hand side. So this side that's upstream, and right-hand side that's downstream. So we find the upstream toe, and then project the point to the water surface. We get the point C, and through the point C, we draw a horizontal line, and it intersect with the dam slope at point A. And then according to the relationship with AB equal to 0.3 AC, then we are able to find point B, because we know the point, currently we know the AC position. So we are able to find the B point. That means AB equal to 0.3 AC. So by now, we can find the point B already. And then next, we can draw a parabola through this point B with the focus at the point D. So this is the focus of the parabola. So this is defined by x equals to z squared minus p squared divided by 2p, and p also equals to square root of d squared plus h squared minus d. So we set this z equal to 0 within this formula. Then we are able to get x equal to -5p. -5p. So by now we are able to get the horizontal coordinate of the point E already. So then finally, then we are able to sketch the transition curve from the A. So A, we start at right angle to the slope. So right angle means is perpendicular to the slope. And we are also the know point E already. So this method, mainly we try to find the point B and point A and point E, and try to connect the point A with the point E in the parabola shape. So then we can just roughly plot a smooth transition with the parabola. So this case, previous case, that's the first time with the toe joint, and this is the case with no toe joint. So toe joint is to help with the drainage of the water. So now point D is at the downstream toe. So this is the downstream. So point D, that's the downstream toe. So the phreatic surface emerges at the downstream slope and the point F. So, but we don't know the point F right now. So then we need to try to find the vertical coordinate of the point F. So all the other points will be the same as before. We know the point C, we know the point A, and point B, that's the point 3 relationship. So we know the point B. So the only difference with the previous case is we need to find the vertical distance of MH, and this M we are able to take from this figure. So the horizontal axis, this beta is the angle of the downstream of the dam, and this H over D. So the D, that's the vertical distance, horizontal distance between the point B and the point D, and this H, that's the thickness of the water retained by the upstream. So if we know the beta and H, we're able to find the value of M from this chart. So if value is not, let's say if the value is here, then obviously that's 0.1. So for the other case, we can do roughly do the interpolation between this line and this line. So eventually we are able to find the value of M for any case. So M times H, because H, we know the value for H, so we know that this height already. So then we are able to find, surely we are able to find point F already, because we know the MH. So then we are able to sketch also again from the sketch this phreatic surface also from the point A and draw a roughly smooth curve, and but now it's a tangent, roughly tangent at the point F. So this is the phreatic surface from the A to point F. So this is a case for the earth dam with no toe drain, and previous case that's the earth dam with toe drain, and how we plot the phreatic surface. So this is some cases for your information. But for the majority problem, now we use steel piles or the coffer dam or the concrete dam. So but these type of questions are more quite often, so we're able to calculate the seepage and pore pressure. So now this is a summary of how we draw the flow nets. So I hope you can just follow these general procedures and draw the flow nets. So with a few simple rules and tricks, we could just draw our solutions by hand. So firstly, we plot the problem to be studied to the convenient scale, and the dimension of the length ought to be in proportion. So at least you try to be in proportion and to make it look reasonable. And then we mark all the boundaries and the flow water head and pressure condition to each boundary. Let's say we label the upstream water height and downstream water height, and also we need to label the delta. So we know where we take the reference. And next, we could plot a course net, which needs to meet two requirements. So firstly, it's consistent with the boundary condition, and then with flow lines and equipotential lines orthogonal. So this means they intercept at 90 degrees. So normally we will start to draw the flow lines according to the pattern or tendency of the flow. So you don't need to draw too many flow lines because that will be quite time consuming. So normally 2 to 4 flow lines or roughly 3 or 4 flow lines, that's adequate for the majority of the case. And afterwards, we can modify the flow lines to satisfy the point 3 and make sure that elemental rectangles have a consistent length to breadth ratio as 1. So, and finally, we are able to refine the mesh to create a more reasonable plot. So these are the general procedures. I hope you will follow to draw the flow lines. And that's a really important part of this lecture.
So a quick question.
Yeah.
Before you continue, we have the makeup practical classes for Easter Monday today.
It's 12 to 2 and 2 to 4.
As per what was on Easter Monday.
Yes, that's cover for Easter Monday.
Thank you.
Now we go to some interesting part. So I would like to show you 2 examples to help you to better understand how we draw the flow nets and how we just do the calculation accordingly. That's really important. So I hope you just pay more attention to it. 2 examples. So the first one, the figure below shows a cross section through a long excavation in fine sand. So the permeability K that's given is 1.5 times 10 to the power of -4 meter per second. So this excavation means we just install some steel sheet piles. So that's the one pile, that's another pile. And then we dig some soil out. So that's the dig some soil out. So that's the original soil surface, then 0. And obviously there are 2 meters of water above the ground. And also this type of structure is called the coffer dam. We are required to estimate the rate per meter length of excavation at which the water must be removed from the flow of the excavation in order to prevent flooding. So in other words, we are required to calculate the seepage Q. So because it's prevent flooding, which means we need to maintain the water just at this excavation level. Otherwise, if your water level just raise up to this level, it means this excavation is already flooded. So we have to just do the calculation at this critical scenario or critical point. So the first step, like I said before, so we need to, when we make some drawing, we need to label the dimensions. So we know the soil surface, then 0. And from the soil surface to the excavation, that's 40 meters. And from the excavation to the bottom of the sheet pile, that's 7 meters. And from the bottom of this pile to the impermeable layer, that's another 7 meters as well. So, and we have 2 meters of water. So we try to label those dimensions on the chart. And next, we need to find the delta. So obviously, like I said before, delta is normally set as the downstream, the level of the downstream. So for this case, obviously this is the upstream and this is the downstream case, because there's a tendency for water to flow this way and into this excavation. So that's the delta. And then next, we label the water height value at the downstream, upstream, and downstream. So for the downstream, obviously, if it's not flooded, then the water height will H, that's 0. That's obvious. And upstream water height, that's I already provided the value of 16. Can you? I wonder, you know how to calculate that right now? Because we already show you the equations long time ago. So H equal to UW divided by gamma W plus Z. So this pressure height. So what's the value for pressure height for any point on the upstream? So what's the value for pressure height?
0.
0.
No, it's not 0. Upstream.
-2.
No, the Z. No. The datum is here. So that's the datum.
14. Wait.
So no. So the pressure height. So pressure height. So you have to know the definition of the pressure height. That will be the water pressure acting. The height of the water pressure acting on this point. So that will be 2.
Oh, yes.
So it will be 2, and then the elevation height. Elevation height, it only has a correlation. I repeat multiple times. Elevation height only has a correlation with the datum 0. So that's the datum 0. So what's the elevation height?
14.
Yeah, that's right. So that's 14. So 2 plus 14 gives you 16. So I label 16 here, but you need to know why we get this value. So according to this total height formula, we get the value of 16. So is that clear now? 16?
Yeah.
Yeah. And then since we get the datum, we know the water height upstream, downstream. The next step, we start to draw the flow lines. So we draw the flow lines first. So this is roughly just based on the common sense. So we know there's a tendency of flow line. So we draw the first flow line this way, and then we draw a second flow line. So for this case, we just only plot 2, and that will suffice. So only 2 flow line. Yeah.
How do you know, like, so like, how do you know if it goes from that point to that point, to where it goes from this point to over here? So how would you know what angle it goes into it?
This one, you see, just based some experience.
So how do you assume that? Yeah.
No, this is just based some experience. So it has to, because that's the symmetric. So it has to be, if you want to draw more flow lines, it has to be the first one go to the left hand side, and second one go to the right hand side. But but you can just add more flow lines. So if you add another one, then that's fine. So your equipotential line will meet the rule. I will just explain later on. Now let's look at only 2 flow lines. So if you would like to draw the equipotential line, so that's the first equivalent line. That's why we plot this way, because we have to meet all these requirements. They form a right angle with the flow line. So that's the right angle. That's the right angle. Remember in the previous, yeah.
If you drew like so one going down here, then you drew like, wait, sorry, that's bad drawing. So if you drew the one going down here, yeah, the one going there, for example, the one going here, no matter what, you're still correct.
Well, I not quite fully.
Or you have to draw it. Okay, so yeah. Okay,
so
divide.
Yeah,
like,
so you have to. So you have to make it. You see, just let me just finish this. Let me finish. So you have to certify. You have to meet the requirement. They roughly form a right angle, and this block has to be a square, roughly a square. So you can just plot another one here, right? But this shape, that won't be a square. That's a right angle. So that's why you have to start from here, this point. You can't start from this point, because this shape will be a rectangle. That's not a square.
Yeah, kind of like so. If I'm saying this, like I'm saying, for example, if I draw 5 flow lines, so there's one there, then I have one here, then I have one here, to that stuff, right? Like then I draw the lines going, wait, so then after that, like draw these lines going here, doesn't matter
Yeah, it
how many
doesn't
lines we
matter.
draw.
Yeah,
Oh,
yeah,
okay. Oh,
I just try to explain maybe
Okay.
later on. Can you just erase that one?
Yeah.
What I mean, so let me just finish and then maybe I will cover that. So we have to meet the requirement. They have to be the right angle, and also it's roughly a square area. So we follow the same way. You see, that's the right angle. That's the right angle. By the way, you see, this is the impermeable. This part, you see, is pale. So that's steel. So that's impermeable layer. And this part, that's permeable soil. So obviously, this will be a flow line. So that's why flow line and equipotential line, they form a right angle. And we try to make a square shape. So that's why I add another equipotential line here and right angle. So follow the same way, I add more equipotential lines. So this is roughly how the flow net in the left-hand side looks like, because it's symmetric. So the right-hand side, the flow net will be the same. So now I would like to maybe try to cover your questions. So it doesn't matter. So if you would like to add another flow line, so let's say I don't plot this way. So I plot from here.
Yeah.
Here, and then I
that's all right.
Plot another one. Yeah, that's okay. So I add another one here as well. Yeah. Another one here as well. So this way, maybe I try 1, 2, 3, 4, 5, or 6 plot. But here, the equipotential line you can't plot here because that's right angle. So you have to draw the equipotential line. Yeah. So that's fine. So when you will realize when you do the calculation for the C page, the result will be similar. So when you attend the assessment, as long as your flow net looks reasonable and your result is not a huge difference with the right answer, then you won't lose any mark. But you have to meet, obviously,
the requirements.
You have to meet the requirement.
It's right angle and square.
Yeah, right angle and square. That's right.
So if we draw some extra lines, so we have to get some extra line for the ring one, right?
Yeah. What's up? Okay, let me just remove it. So which means there's no absolute one answer. So there are multiple answers as long as your plot looks reasonable. But like, as I said, so to try to save time, normally you just plot 2 to 4 flow lines. That's enough. 2 to 4 flow lines, and you can draw the equipotential lines. So maybe roughly for majority case, you just plot 3 flow lines. That's already sufficient. Otherwise, if you just plot, let's say 4 or 5 flow lines, then you have to plot the same amount of equipotential lines. So that's really taking more time, and you need to take time to refine the match or the element. And next, so once we get the flow net, next we are able to do the calculation for Q. So here, because the upstream, the water height is 16, and downstream water height is 0. So the height difference, that's 16 meter. Next, we count the NF, because we try to calculate the Q and all these other elements within the Q formula. So NF, that's the number of flow tubes. So we can count from anywhere. So that's 1, 2, 3, or 1, 2, 3 anywhere. So that's the number of flow tubes. But here, but because it's symmetric, so the right-hand side, we have another 3 flow tubes. So you have to times 2. So here you have to be careful. So for some assessment, you may forget to times 2 for the symmetric problem. Because if the problem is in symmetry and you only plot the left-hand side or right-hand side, remember to times 2 gives you the total number of flow tubes. Yeah.
So if I had, for example, like one flow line going down here, and I had one going down there, one down here as well, that means that's how I have 1, 2, 3, 4. So it will be 4 times 2 for the number of flow tubes. Oh, okay. Sweet.
And then the number of head jobs. Again, you see, this is the initial head, and then we count the head job. So that will be the first head job, right? First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. 13. So in total, we have 13 head jobs. So no problem right now, right? And then that's the CPage formula to calculate the CPage. So we know so this K is already given. K is given, and we know the NF, ND, and delta H, that's 16. So eventually we get this value. So that's in terms cubic meter per second per meter of excavation.
What is the NF measure form again? Can you repeat that, please?
So NF, that's the number of flow tubes. You see, you count 1, 2, 3,
Yeah.
or 1, 2, 3. So that's the number of flow tube. So
Yeah.
because it's asymmetric, so in the right-hand side, you will have another 3 flow tubes as well. So one,
Okay.
yeah.
You
So
also take in consideration that it's for both sides, so you multiply by
yeah. Because you plot only the left-hand side or right-hand side, so you have to times 2. Because in reality, the 6. So here you have to be careful. For some questions, it's asymmetric, so you have to times 2. Now I will show you why you have different flow lines, but your result will be the same. So let's say if you have more flow lines, then your number of flow tubes will increase. So this NF will increase. And actually this number of, because you have more flow lines and more equipotential lines, and the number of head jobs, ND will increase as well. So eventually the ratio that will be canceled out. So this NF, ND for the different type of flow lines, the ratio will be similar. So that's why you get the same answer or similar answer. You know what I mean? Because the K and their edge constant. So if you increase in NF, then ND will increase as well.
excuse me, sorry. If you take in consideration the other side, why you take in consideration for ND too? Because I believe
No, ND is the head job. So you see either from this side, the right hand side or left hand side, it will be the same. So the right hand side will be 3. It will be 13 as well.
But don't you have to multiply by 2 because that will give you, it's like you take in consideration both sides?
No. This one no need, because that's only the head job. That's not flow tubes. Flow tubes, you see that's the left hand side, right hand side. So you have to consider the sum of both sides. But head job is only just only relative level from the upstream to the downstream. So you only need to use one value. That's it.
Sir.
Yeah.
So let's say this was a question in the exam or whatever. Would
Yeah.
everybody get the exact same answer? Because let's say I
see,
draw
that's-
it and I do 12 instead of 13 and somebody does 14.
Yeah, that's what I said. You see, if as long as your answer is not crazy different, then that ought to be fine. So if your answer maybe 0.1, 0.3, or you see 0.95 times 10 to the power of -3, that ought to be fine. Because this value, that's from your flow net, that will be 6, and then ND, that's maybe 15. So the ratio may be different, but only slight difference. As long as within the allowable range, then that ought to be fine. Because we allow some human error involved in the hand calculation. That's unavoidable. May I continue or any other questions?
Yeah, so if you continue, please.
Yeah, okay. So next, we just go for another example. That's a really important one example as well. So we are required to determine the quantity of seepage Q under the concrete dam. So because previous one, I think the previous one, that's coffer dam, that's steel. So we don't need to plot the phreatic surface because that's only the earth dam. It has this issue. And this is a concrete dam as well. So we don't need to plot the phreatic surface as well because no water can flow through the concrete in general. So, so this is the concrete dam. And we need to firstly calculate the quantity or the seepage, and then we plot the uplift pressure, means the pore water pressure. So we need, the second question is, we need to plot the pore water pressure distribution on the base of the dam. So that's obviously this is the dam. So that's the base of the dam. So we need to plot the pore water pressure U on the base of the dam. And coefficient of permeability K, that's given this value. So Q, obviously we still use the previous formula. And for pore water pressure, we just take some special point, and then just take the value. So we just take 5 or 6 points and then take the value and then just connect together. That means the distribution of the pore water pressure. So again, for this case, the dimensions has been given, and this is a reasonable scale plot. So this is water. So this case, that's the water upstream, that's 50 meters, and that's the soil surface, and that's the soil surface. So it's the level of, and the water downstream, that's 2 meters above the soil surface, and the dam, that's 2 meters below the ground. And here, in the right-hand side, there's a pile that's below the 50 meters below the ground. So that's roughly the dimension of this problem. So again, after we label the dimensions, we put the datum. So the datum normally just aligns with the water level down, the ground surface downstream. So you see that's the datum. So datum aligns with the ground surface downstream, because that's easy for calculation. So for this case, the water level upstream, that will be 50 meters, and water level downstream, the water head upstream, that's 50 meters, water head downstream, that's 50 meters. So by now you already know why we get this 15, right?
Yep.
Can you just explain why we get this 15? Plus C. So what's the UW? So what's the pressure head value?
2.
So what's the pressure head value?
2.
No, upstream.
15.
Yeah, upstream water head level. So it's only the water, the distance between the water to the upstream water surface, upstream soil surface. So that's 15, and plus the elevation height. So what's the elevation height? Because this point aligned with the datum. So elevation height, that's 0. So that's 15.
0.
So how about for this case?
U equals to 2.
Yeah, E equals 2. So what's the pressure height?
U equals to U equals to 2.
Yeah. So
And Z equals to 0.
Yeah, that's right. So we have to understand why we get this value. It's not only 2 meters above this one, then you get 2. So you have to consider this formula and get the right value. So the Z, that's all aligned with datum. So that's why the elevation height is 0. So if Z is here, then that will be -2.
Yep.
And pressure height is only the water surface to the current position you want to calculate. So next, since we get the datum, we get the water height. Then what's next? We need to draw the flow lines. So now maybe after we draw the flow lines, we need to calculate the pore water pressure. So I just label 5 typical points underneath the dam. So if you like, you can add more points, but the shape will be similar. So I just take 5 critical points. So 3 points align with the 2 corners of the dam, and then another 3 points that evenly divide the bottom lines by 4 parts. So once we get, yeah.
Sorry, sir.
Yeah.
Can I ask you this? So about the points, so we can choose as many as we want, right?
Yeah. The more points, the more accurate your result or your plot.
All right, and then like the number of points that we have to divide them, they have to equal each other, right? First of all,
it's better to be equal. Yeah, it's better to be equal.
All right.
Yeah. And then we can start to draw the flow lines. So you see this one, I take 5. So if you like, you can take 7, 8, or 10 points, whatever you like. But eventually, the distribution curve will be similar. So now we draw the first flow line. So we start from the upstream. So now it is actually this direction, flow from this direction, and then we plot a second flow line and then third flow line. So you see again for these problems only 3. I previously mentioned 2 to 4 flow lines. So for this one, for the previous question, there's 2 flow lines, And this question, there's 3 flow lines. That will suffice. So if you like, you can make a narrow range. You plot 5 flow lines. That's okay as well. So for this case, we get 3 flow lines. And then if we meet the requirement, the square requirement, and also the right angle requirement roughly. So we can't make exactly the square everywhere. Then we can get the equipotential lines. Equipotential line. Yeah.
Okay, so how do you find 3, 4, 5, 6, 7, 8, 9, 10, and what the other values for
Which
H?
one?
Or so I saw on the screen that over here there was H equals to 3. And
Yeah, this one. So you see, because eventually we need to get the water height. So if this point falls on the water height line, let's say if here there's 4, which means we know the water height 4.1, right? So we try to make the water height go through those points, but it not be necessary go through. We can do the interpolation as well. That's fine as well.
Okay, wait, so to say that the H value over here was 3, then that means that over here that'll be 4 and 5 and 6.
No. We don't calculate that way. So once we get the height difference, the flow length, then we calculate the height difference. Height difference again, you see delta H equals to 15 minus 2, right?
Yeah. So it is 13. Yeah.
30 meter, and then we count the number of head drops, ND number of head drops. So from here start. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So this we know the number of head drops are 13. So N delta H divided by this number of ND delta H divided by ND 13 divided by 13 equal to 1. So which means we know the head drop between each equipotential line, that's 1. Does that make sense? So we know that's equipotential. So the head drop is 1. So now we start from here, that's 15. So that's why we get value 14 here and 13 and 12. And that's 3 here.
In this example, the left side, it's not equal to the right side. Like,
which one?
Like the example before, we did like one side times 2. Now we're gonna do each side by itself.
That's for the flow section. That's for arms and F. The example before 2 times by 2 because the dam was symmetric. But
yeah. Because of, this is not a symmetric. Because you like I said before, if problem is symmetric, then you just only need to plot the half. Because this is not symmetric, so we already plot the whole flow chart. You see, that's the whole flow net. For previous one, we just plot half. So that's why we have to times 2. Yeah, is that clear?
Yeah. Wait. So let's say that value for delta. Let me think. So to say delta H was 26. Yeah, and then ND was 13.
13, yeah. So that will be 2.
And 2. Exactly, yeah. So that'll be 2. So then that'll be 4, that'll be 6, that'll be 8, that'll be 10. Is that correct?
Yeah, that's right.
Okay. Yes.
Yeah. But here it will be 26.
21, yeah.
Sorry, 28. So because you need the difference of 26. So here it will be 28.
Yeah.
Okay.
Yeah, sweet.
So if that's clear for this one, then maybe we are. So is that clear for this one, the flow net?
Yep.
Previous one, that's a really good question. So because this one, that's asymmetric, so it's not symmetric. So we just need to plot the whole flow net. So when we do the calculation, now we do the calculation for the C page. So the height difference, that's 15 minus 2 is 30 meter. And this number of flow tubes in F. So that's 1, 2, 3.
Why do you draw these numbers here? Or what they do represent?
You see, you can you need to plot the water distribution. So you need to know the value of per water pressure at any point below the dam. So that's for the second question.
Is this number given?
No, it's not given. So you need to calculate the pore water pressure. So currently, firstly, we need to try to know the water head, and then according to one formula to calculate the pore water pressure.
How do you knew it was 5 here instead of 10?
Which one? The
Yeah.
5?
How do
This
you know
one?
there was 5 points in here and in the
No,
concrete?
like I explained previously, it can be 10 point or 20 point, whatever you like. But I just do a demonstration here. So it's flexible, but this one, the distribution chart will be similar. So you can put 10 points or 20 points.
All right. Okay.
Yeah. So I just put some typical point here. So let's with better just continue. So the number of we have another one, 1, 2, 3, 4, 1, 2, 3, 4. So number of flow tubes, that's 4, because it's not symmetric. It's not symmetric, so we don't need to times 2. And number of head drops, 13. We already got the value. So we put the value. We know the K. We know delta H. So that's the first question. The answer for first question, in terms of cubic meter per second. That's Q. And second question. If we know because we need to get this value, the pore water pressure. So we need to try to get the total height and elevation height. So for the previous 5 points, we know so from the equipotential line, we know the value of these 5 points for 5, 6, 7, 7.5. And elevation height, that will be -2. I will show you, maybe go back, we have a look. So for all 5 points, the first point is on this line. So we know the corresponding value, right? The water head value. You see, the total water height, that's 4. And the second point, that's 5. And third point, that's 6. Fourth point, that's 7. And the fifth point is a bit tricky. But we know that's roughly in the middle between the two equipotential lines. So between 7 and 8. So we take average. So we know the water head will be 7.5 meter for this one. So that's total water height for the 5 point. And the elevation height, like I repeated before, the Z only relative to the delta. So that will be -2 for all these points. So that's a constant value. Is that clear? The Z equal to -2.
So we
Sorry,
use
sir.
15 divided
Yeah.
by 2. So we
Yeah.
have 7.5 each.
Yeah.
So about those red lines, so we just measure like 7.5, 7.5, and 7.5, right?
Which one? Which point?
I mean like those red line.
Red line?
Yeah, the flownet. Yeah, you draw. So like how do we divide them respectively?
You mean this one?
Yes, humor.
This one. So this one, you see, you can take interpolation. You see, if the red line, that's in between. You see the distance. That's roughly in the middle of the two equipotential line. Let's say this point. That's in between this one and this one. Then you can take an average. You see?
No, sir. The red line in the flownet.
This one?
Yeah, that one.
This one, you see, you just only take the equipotential line. This has no correlation with the flow line right now.
Right.
So because you need to try to get the water head. So water head only has correlation with the equipotential line. So you only need to read the green line, not the red line.
Oh, so the red line, like we can choose anywhere and then we just draw them.
So you mean the red line?
Yeah, that one.
Yeah. But you have to just you see, based on your just some common sense, you plot three flow lines, 2 to 4 flow lines in roughly in this shape.
Yeah, but about the curve, like we have to follow.
Yeah. You have to follow
the height line.
Yes.
The right hand side goes down 15 meters, so we have to
start from
15 meters.
Yeah.
Oh, all right.
Okay. Sorry. Maybe I'd better just go ahead. So if we have sufficient time, because I have to cover the second half.
Sorry, sir.
So,
the outcome to Z is -2 for each case.
So you see, like I explained previously, the Z is only relative to the delta. You see. Yeah. 2 is here. You see.
Yeah.
So that's a -2 for all the cases. So we know the H, we know the Z, gamma W constant. So we are able to calculate pore water pressure for all 5 points. 1, 2, 3, 4, 5. So now we just put the value on the above point. So that's the pore water pressure, or so-called uplift pressure. And if we connect those 5 points, that's a so-called pore water uplift pressure distribution. So you see, if you add another one, this point obviously will be here, here, here. So the more it will be a more smooth curve if you add more points, but the general trend will be the same. Okay.
Sounds good.
May I just go ahead? So maybe I'd better go ahead. So can anyone have, yeah, remove this one. So if you have any questions, let me see if we have some sufficient time left. So now let's have a look at the flow nets for anisotropic materials. So some soils are placed by horizontal deposition. Because of seasonal variations, this deposit tends to be horizontal layer and have a different permeability in the horizontal plane to the permeability in the vertical direction. So in the first part of lecture, the materials are isotropic, so which means the property of the material are the same and independent of the direction. So for the anisotropic materials, they are direction dependent. For example, the KH, so and KH and KV are different. So which means the permeability, the horizontal permeability and vertical permeability will be different. So that's so-called anisotropic materials. So if we consider horizontally layered deposit, as shown in this figure, it consists of a pair of layers, so 2 layers. So first of which, it has a permeability of K1 and thickness of D1, and it overlies the second layer has a permeability of K2 and thickness of D2. So for this 2-layer system, according to the Darcy's law, so dirt H, so V1 equals to K1 times dirt H divided by dirt L. And also we have this Q formula, dirt Q1 equal to K1. So Q equal to VA, actually V1 times A. So equals to V1 is this one, and A, that's the D1 times unit weight, so that's a D1. So similarly, for the layer 2, we have the similar expression as well. So therefore, for the equivalent system comprising the layer 1 and layer 2, the V equals to Q over, so for the 2-layer system, the V equals to Q divided by D and equals to Q1 plus Q2. So that's the quantity for the first layer and second layer, and the sum together and divided by the total thickness and equals to KH times dirt H divided by dirt L. So this KH could be expressed as D1 minus D times K1 plus D2 divided by D times K2. So this KH is called weighted arithmetic average of the permeability. So this is one definition of KH. So that's only for the horizontal permeability. So
Wait, so
yeah.
so what's what's KH? To KH the weighted arithmetic average, or is KH the horizontal permeability? I'm confused.
So this KH, that's the equivalent permeability of the 2 layered system. So that's the equivalent one. So that's one.
So based upon 2 of them. Yeah.
So that's the equivalent permeability of the 2-layer system, roughly. So now, previously we considered the 2-layer system. Now this previously KH equation could be generalized to 3-layer, to 5-layer, or even to 10 layers. So we just add another term. So if 3-layer, then this will be D3 divided by D times K3. So, and also this KH, there will be weighted arithmetic average of the permeabilities of the layers. So either 3 layers, 5 layers, or 10 layers. So this will be one expression. So that's the equivalent horizontal permeability. Now let's have a look after considering the horizontal flow, let's have a look the vertical flow. So previously water flow this way. Now the water flow from this way. So we have the height difference. So the top part, the water height is H0, and then you have a height difference delta H1, and for another layer you have a height difference delta H2. So there's a tendency for water to flow downward. So again, from the Darcy's law, we have the V1 equals to K1 times delta H1 divided by D1. So if we do the transformation, this is the expression for delta H1. So the expression for the height drop. And for layer 2, again, we have the expression for the height drop as well, delta H2. So if the total height drop will be obviously delta H1 and plus delta H2. So if we iterate those two formulas into this one, here is the expression. So the total layer system. So again, we try to introduce again as the horizontal permeability. So we introduce another one, the vertical permeability, KV. So, and this is the expression for KV. So because the KV will be some form of the, so KV will be some form of the D1, D2, and K1, K2, and D. So that's the KV expression. And this KV is called weighted harmonic average of the permeability of the layer system. So that's this KV will be the weighted average of this two-layer system. Weighted harmonic average, yeah.
This D, like so D1 plus D2.
Yeah.
Okay, so so say we had like 1, 2, 3. So we have D1 and we have D2 and D3.
Yeah.
D will be the sum of D and.
Yeah. So you see, what you say, you see, you already just make a plot for here. You see, we have the D1, D2, D3 until the Dn. So we just add more terms. So if, if a 3-layer, we just make n equal to 3. So this formula, we just add a term, add another term, or reduce another term.
Yeah.
So in conclusion, this KV, this will be weighted harmonic average of the permeability of the whole layer system. So that's the two formulas, one for KH and one for KV, and for multiple layer system. Now let's have a look at one example. So suppose the layers shown in the figure of equal thickness. So this will be D1, D1 and D2, they have the same thickness. So they all equals to D0. And the K1 and K2 will be different. So if K1 and K2 are the same, we call it anisotropic materials because they are different. So we need to calculate the KH and all the equivalent KH and KV for the two-layer for this new one-layer system. So we just iterate all the given values to the formula. It's quite straightforward. D1, D2 equal to D0, and K1 value is given, K2 value is given. So firstly, we calculate KH. We know this is the expression for KH, and we know D1. We know D1. We know the D2, and D is the sum of D1 and D2. So that's 2D0, and we know K1 and K2. So we can easily get the value for KH, and that's the expression for the KV. So again, we can easily get the value for KV as well according to this this expression. So if we have another layer, the third layer, then we just add another term to do the calculation as well. So I think this is quite straightforward, right? So maybe I can just go ahead. So next is the Flownets for anisotropic materials. So recall in lecture 3, the steady state flow in an anisotropic material having a horizontal permeability of KH and vertical permeability of KV is governed by this equation. So what we need to do is transfer the anisotropic case to the equivalent isotropic case. Because when we draw the flow net for anisotropic materials, we can't draw it straight away because the permeability are not the same. So the original rules and policy doesn't work for an anisotropic. So we have to try to convert to the equivalent anisotropic case, and then we are able to draw the flow nets and do the calculation, like calculate the seepage or the water pressure. So the solution of this equation can be reduced to that flow in an isotropic material by the following simple conversion. So we introduce the new coordinate variables defined as this. So x equals to alpha times x bar and z equal to z bar. Then the flow equation becomes this. So basically we just divide by kh, divide kv, use kh divided by kv. So that's this expression. And if we set alpha equals to square root of kh over kv, or kh over alpha squared times kv equals to 1, then the equation, the previous equation for an anisotropic material could be reduced to that one for the isotropic material, right? So the flow in an anisotropic soil can be analyzed using the same method as that used for analyzing isotropic soils, and also including the sketching of the flow lines. Note that the equivalent isotropic permeability for the transformed soil is now the KEQ, and it's the square root of KH times KV, KH times KV. Postulated formula will be covered in the next slide. So this is the method we try to convert from the anisotropic to the isotropic cases, and then all the following parts will be the same as we covered in the first lecture, in the first half of the lecture. We already mentioned that. So convert from the anisotropic to the isotropic by this type of transformation. So if we look at this example, so because the KH and KV, they are different. You see KH equals to 4 kV. So that's why we call it an anisotropic material. For the, if you check the previous questions, it's all just only one permeability, the K is given. So that means the KH and KV are the same. So we have only one value, and that's isotropic soil. But from now on, we have an anisotropic soil. So if we, you have to read the questions carefully. If KH and KV are different, then an anisotropic case, you have to do the conversion first. So we are required to calculate the flow under the dam as shown in this figure. So we are required to calculate the Q, so the KV and KH and H1, H2. So water head upstream and downstream are given, and permeability coefficient are given as well. So firstly, we need to calculate alpha. So alpha, that will be the square root of KH divided by KV. So because KH equals to 4 kV, so we can easily get alpha equals 2. And also from the previous slides, x equal to alpha x bar. So here s equal to 2 times s bar and z equal to z bar. But we need to do the conversion. We need to express s bar and z bar in terms of the original coordinate. So these are the new coordinate system that we need to plot for the isotropic material. And that's the original. So that's the anisotropic. So this is isotropic coordinate system. So now now we are able to do the convert. So that's the original anisotropic layer system. Now with this relationship, we are able to convert to the equivalent. So they are equivalent isotropic system. So what has changed? So So we go to the Z. Z is the vertical direction. You see here, Z is the vertical direction, and in this coordinate, that will be x, Z bar, S bar. So only the horizontal coordinate that changed. So it's all reduced by half. So you see, the length of the dam, that's L. So now the length of the dam was reduced to the half length. So the only difference will be here. The other parts, the water height upstream and downstream will be the same, we maintain the same. And another difference will be we need to use the equivalent permeability coefficient to do the calculation. So that's its expression. So, and now since we get the equivalent isotropic Flownets, so equivalent isotropic system, we can draw the Flownets. So that's how the Flownets looks like. So we have the flow length and equal potential length. It's already provided in this figure, in the bottom figure here. So according to this this figure, the Flownets figure, then we are able to use this formula to do the calculation. So that's quite similar as before. So only difference is we need to use the equivalent permeability coefficient, the KEQ, and KEQ equal to square root of KH times KB. And again, the height difference, that's a difference of 13 and 2.5, and number of flow tubes. So we can count 1, 2, 3, 4, 5, 6. Number of flow tubes, so NF, that's 6, and number of head jobs, so that's the upstream, that's the downstream, so that's the downstream, and that's the first water head line, and that's the last water head line. So the head job will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the number of head jobs. So this maybe we'd better change to ND. So NH and ND are equivalent, but we can use ND. So number of head jobs ND, because that will be consistent with the previous slides. ND, that's a 14. And KEQ, because we know KH, KV, we are able to get the value of KEQ. So we iterate all the values into this formula. So here is the final answer. So that's per unit width of the dam. For a dam of 50 meter. So I wonder if I already explained maybe a few times. So that's 1 per unit width. Well, for this dam, you see it's for the direction perpendicular to the screen, the length. We are required to do the calculation for 50 meter. So we need to times 50 to the original Q. So 50 times this value. So that will be the final answer. So you can either express as cubic meter per second, or you're able to convert to per day. So both answers are the same, are equivalent. So any question for this one? Otherwise, I need to go ahead.
This is how much water comes out, filtrate underground per day.
Yeah.
This is the value of how much water is escaping from the original dam. But what happened with the years when those tubes become bigger?
So this one, for these questions, you just assume the tubes maintain the constant. So as long as the water height will remain the same, the water difference remain the same, then you have to, so it has some theory assumption. If the water height remain the same, then the flow net will remain the same as well. So we can't consider that way when the shape change, the flow net shape change.
Okay, yeah, because in the real world, summertime the water level drops, and also
no. You see, when the water level drops, then you have to plot a new just a flow chart and do the calculation.
All right, thanks.
Yeah, and then maybe I'd better just maybe try to spend more time to cover the. So I think maybe this is the last few slides. So for this is cover the problem for the internal erosion. So it's also called the piping. So this occurs in many dams. So it's mainly for the earth dam. Many dams, earth dams. So it happens when the effective stress of the soil reduced to zero. So we call it the quick condition. We call it the quick condition. And also the water carried soil particles away from the dams. So as the stored water rushes out the channel, the flow channel widens, and eventually the catastrophic failure may occur. So piping is most likely to occur at the toe of the dam. So that's the downstream. So that's the toe of the dam. So piping is more likely to occur around this position. So as shown in this figure, the hydraulic gradient at the top of the dam can be obtained from the flow net. So once we get the flow net, we are able to calculate the I. So for this case, the saturated unit weight of the soil is given. So that will be 18 kilonewton per cubic meter. So that's given. So from the figure, the head drop. So we just take the head drop between the second to last water head and the last water head. The head drop, that's the 0.75. So this is taken from here, actually. So that's the zoom in of this area. So the head difference, their hedge, that's 0.75 meter. And the vertical distance, delta Z, equal to 1.125 meter. Here, this vertical distance, we just roughly take an average, because the distance, average of the vertical distance from here to here and from here to here. So we roughly take an average. So that would be the average of the whole block. For some other cases, if you have a square shape, then this delta L. So this is the delta L. Then this delta L is just this length. But this one, because it's a bit irregular shape, so we just take an average of the length. So delta Z equal to delta L. That's 1.125 meter, because I equal to delta H divided by delta L. So the hydraulic gradient, that's 1.67. So therefore, the critical hydraulic gradient, the IC, here we have one definition. IC equal to the submerged unit weight of soil divided by the unit weight of water, because we know the saturated one. So gamma SAT minus gamma W. So that's a submerged, or what's the other term? Submerged unit weight of soil. Yeah, or effective unit weight of soil. So it's the same. So that's the difference of 18 and 9.8. So we get the ratio of 0.84. So which means if the hydraulic gradient reach this one, then the soil piping, then the piping would occur. Then the effective stress of the soil here at this area will be zero. So the soil will behave like water, so it flow anywhere. So piping will occur. So once the I, so we need to compare this I and this I value. So it's this I value that's greater than this one, which means there's no risk for the piping to occur. Otherwise, the piping already occurred. So here we introduce another factor of safety, FOS, that's equal to IC divided by I. So 1.82 divided by 0.67. So we get a ratio of 1.62. So if this value that's greater than 1, which means there's no potential, no risk for quick condition or piping or effective stress to zero. That's the same thing. So if this ratio equal to 1, which means it's on the verge of the quick condition. If this less than 1, which means the piping already occurred. So if this gradient, the calculated gradient from Flownets, that's greater than the critical gradient, which means the piping already occurred. Now we have the 15 minutes. I would like to just cover the last question. So this will be another important example as well. So And also that piping and calculation, quick condition calculation was covered here as well. So it is proposed to dewater the coffer dam by lowering the water levels inside it. So that's the original water level. So we insert the steel sheet pile and then dewater, and then take some soil, excavate the soil, and that will be the ground, the soil surface within the sheet pile. That's the so-called excavation. So we would like to, we need to investigate the suitability of this proposal by means of carefully sketched flow net. So we are required to draw the flow net on an appropriately transformed cross section. So what is the, so that's the first question. And then what's the flow per meter width of the coffer dam? That will be the second question. So we are required to calculate the seepage actually. And then what's the factor of safety against the quick condition if the saturated unit weight of the soil, gamma SAT, that's 19. So the third question, sub question, we are required to calculate FOS. So when you look at this one plot, so what you can tell from this one? So the dimensions is already given. I think that's the soil surface behind the sheet pile. That's the soil surface, and water that's 6 meters below it, above it, and this is the ground within the sheet pile. So that's 6 meters below the ground, and the bottom of sheet pile that's 6 meters, and there's another 6 meters from the bottom of the sheet pile to the impermeable layer, and here is layer design, KH and KV are given. So what you can, when you read these questions, so what's your first information you can get?
Symmetric. So it's 1 by 2.
Yeah, that's a good point. So it's symmetric. So obviously, we only need to plot the flow net only the left hand side or right hand side. That's it. But we need to multiply the flow tubes by 2. There's actually another important information given in this question.
The height difference is the same, I think.
No, it's not. Height difference will be, yeah, it will be the same. So another important one will be here. So in the first half, if you go back and read the question, it's only
find
one.
K equivalent.
It's only 1K as a given. So 1K means it's isotropic problem. But for this case, you see there's some implicit information. So it's KH and KV are different. So that's anisotropic. So this is we need to do we need to just find some implicit information. So you have to find the KH and KV, whether they are the same or not. If only one value is given, then isotropic. You can draw the flow net straight away. But for this case, we have to do the conversion. Otherwise, we are not able to draw the flow net and do the calculation for question 1, 2, 3. So just follow the previous method. We just find the alpha and then convert from the anisotropic to the anisotropic case. So now we do the calculation. So because KH and KV are not the same, so it's anisotropic soil. So the coordinate transformation is required. So we have to transfer the coordinate from the original xz to the new x bar and z bar. So that will be the new equivalent anisotropic case. So here is how we do the transformation. We know this expression are the same for all the cases. So what we need to do is just get alpha. Well, we know the alpha, that's the square root of KH divided by KV, and KH KV value is already given in the question. So for this case, alpha equal to 2. So we know x equal to 2 times x bar. So x bar, that's half x, and z bar, that's z. And again, this x, z, and original coordinates, and s bar, z bar, and transform coordinate. So we need to make a plot on this transformed coordinate equivalent coordinate. So which means this length original, if original length here from here is 12. So what's the new length here?
Be 6, wouldn't it?
Yeah, that would be 6. That's right. So you see in this, you see, if we normally, so now we take the half of the problem because it's magic. So originally from here to here, that's 12. So actually for this case, it will be 6 meters here. And next, again, all will be the same as the previous anisotropic problem. So we just label the dimensions and Durham and water height. So for this case, we just take a Durham here. So that will be the boundary between the soil and impermeable layer. But if you take a Durham here, the result will be the same as I explained previously. So once we label the Durham, next it will be the water height. So water height, I think originally we have 6 meters here, 6 meters here. So vertical coordinate, those transform coordinate doesn't affect the vertical dimensions because Z wasn't affected. So we have 6 meters, 6 meters, 6 meters, and 6 meters here. So now you should know very clearly why we get value 24 here, right? UW divided by, again, divided by W plus Z. So what's the pressure height value for this level? If Durham is here.
24.
It's like 6 with this extra 6. How we get 24? Or we start?
No. You see, I try to ask you this one because I explained multiple times before. So it will be the sum of the pressure height and water height.
So UW 24.
So UW divided by W, that's water height. So what's the water height value?
So this one's gonna be like 18 plus 6.
Oh no, the water level is 6.
Yeah, that's
Yeah,
right.
8
That's right.
plus
So
18.
water level is 6, and Z,
It's
I repeat over 3 times. Z only relative to the Durham. So Z will be 6 plus 6 plus 6, 18. So that's 24. So hopefully for any future assessment, I don't want you to make any mistakes for the calculation of such problems. It's quite important. So that's 6 plus 18, that's 12. And how about this one? Can you tell me how we get 12? Here. Why we get 12?
Because there's 2 sides.
No, the 12 will be the water pressure height plus elevation height. Why we get the value of 12? So what's the magnitude of 2 components? Because here, that's the water surface. Here, the pressure height will be 0. Here, no water on top. So pressure height is 0. And we only have the elevation height. So that's 12.
Plus 12, yeah.
Yeah. So here, so I think maybe we need to spend more time to get better understanding. Now, all the content will be similar as before. So we plot 2 flow lines. And then we plot the equipotential line accordingly. So the right angle and square block. So we plot the equipotential line. And then because we know the height difference, their hedge will be 24 minus 12. So that will be 12 meters. And we know the height drop 1, 2, 3, 4, 5, 6, 7, 8. So it will be 12 divided by 8. So what's that? So that's 1.5, right? So that's 2, 3, that's 1.5 meter. So the height drop will be 1.5 meter. So 24 minus 1.5, we get 22.5. 8 minus 1.5 again, we get 25 meter. So that's how we get the height drop for each equipotential line. Now we are able to do the calculation for the C page. So this, by now, we already complete the first question. So we draw the flow lines. So the half flow lines, that's already fine because we can label is symmetric. The right hand side or left hand side will be the same. And equivalent coefficient, because we know KH, KV, so that's the KEQ value. And height difference, I already mentioned that that's 12. And number of flow tubes. Number of flow tubes, because that's 1, 2, 3 is symmetric. So we have to times 2 here. Here. So 1, 2, 3, or 1, 2, 3, 3 times 2. So because symmetric, you have to times 2. The number of head jobs, that's 8. So we put the value into the Q formula. That's the value for the C page, because we know the KEQ, NF, and D, delta H. Next is 2. So that's already. So this is the answer. Left hand side, that's the answer for the first question, and that's for the second question. And the last one, we calculate the factor of safety. So factor of safety, like I covered in the previous slide, we have to take this section. So the toe of the dam or the section around the downstream. So only this part. So we need firstly we need to take the hydraulic gradient at the base of the excavation. So I equal to delta H. So delta H is 13.5 minus 12. So that's 1.5 minus delta L. Delta L will be the vertical distance because we draw the flow lines. You see, it has roughly three equal potential lines. So roughly these lines will be 1/3 the total length. So because we know the total length is 6 meters. We know the total length that's 6 meters here. So 1/3, we know the total length here. Also previously I labeled at 6 meters. So 1/3 is roughly 2 meters. So we know the gradient by now. That's 0.75. That's 0.75. And because the saturated unit weight that's given, so we are able to calculate IC easily. So the value will be 0.937. And the factor of safety, that will be the ratio of IC and I. So IC and I. So that's the value for IC. That's the value for I. And for this block, so the factor of safety, that's 1.25. That's greater than 1. So we know this part is safe. So there's no risk of piping. So that's the answer for the second part. Okay, I think that's the end of the lecture today. Any questions for this one? No question for this one?
I'm still not sure how you're getting the for the green H, the different meters. How are you calculating that?
So you see the height difference is delta H is 12 meters. Have you got that? So have you got the height difference delta H?
Yeah.
This here, right? And then you count the number of height jobs. That will be 8 height jobs.
No, I mean the where you've written it in green.
Yeah. I'm just trying to go to that one. You see,
Okay.
Delta H divided by ND, that will be 12 divided by 8. That's 1.5. That means there's a height job between any two equipotential lines. So the difference will be 1.5 between this one, and 1.5 between this one and this one. So if you use 25 minus 1.5, you get value of 22.5.
Okay, thank you.
Yeah.
Yeah. The 2 on the NF, how are you getting the 2 again?
Which one?
On NF, the 2.
No,
2 times 3.
No, 2, that's symmetric. That's symmetric. So when you see that's the same as previous question example. In the right hand side, you have the same flow tube as well. You have another 3 flow tube as well. So it's ought to be 3 plus 3 because it's symmetric problem.
Oh, okay.
So if we no other questions, then just thank you for your attention, and I hope you guys have a wonderful day. Maybe I'd better end this lecture now.
All right. Thank you.